So hello everyone, we are learning the subject of circuit theory or network analysis. We are on the chapter of your fifth chapter, that is of a two-port network. We are learning the last topic content of your the two-port network. That is nothing but your the poles and the zeros, or you can say yesterday we have seen that is nothing but your the transfer functions. So today we will continue the transfer functions along with your the poles and zeros. So in the transfer function, yesterday also we have seen in the last session, that is nothing but in the transfer function. So what we are doing, we have observed how the Laplace transforms, conversation, how the ratio we can get from the output to the input ports or the terminals. So here we will see again go through how we are getting that transfer function. So in short, you can say transfer functions are nothing but which is used to describe the network which have at least the two poles, that we are aware from that, and which are related to your the voltage and the currents. So obviously whenever you are talking about the ports or the input port and the output port, the sources are nothing but your the voltage as well as the current. So we always remember the terminals which are connected. So we are indirectly talking about the voltage and the current. Ultimate, that is nothing but the power. So in short, you can say the voltage as well as the currents are the sources which are connected. The voltage flow potential will be across that network or the circuit, and the current which is flowing through the network. And we are interested to find out how much amount for the current which is flowing in the network along with your the potential across that network from the input as well as the output side. So the ratio is nothing but your the transfer function in terms of the Laplace transformation. So the ratio will be in terms of the voltage, the ratio will be in terms of the current, the ratio will be in terms of the impedances and all. So here the cases are nothing but if you are representing your the transfer function, that is denoted by the g. Okay, so if you're talking about the g of s, if you're talking about the t, that is nothing but in the time domain. If you're talking about the s, that is nothing but you are the s domain, that is nothing but you are the frequency domain. Okay, so here the g is a representation of your the transfer function. Here we written here the 1 2, that is nothing but the terminal 1 and 2. Apostrophe s of this g1 2 is nothing but the terminal 1 and 2. So here if you are talking about the voltage, definitely that is nothing but the ratio of your the output voltage to the input voltage in terms of the frequency domain. Similarly, if you are talking about the 2 and the 1, so at that time you are looking from the opposite direction and you are interested for the ratio of your the input along with your the output, okay, in terms of the frequency domain. Similarly, if you are talking about the current, so at the time the gain or the ratio is nothing but the notation will be your the alpha, that is the 1 2. So here the vice versa case with your the voltage and this one. Okay, so if you're talking about the current gain or the current ratio, at that time the current transformation of the one port to the other port, that you can calculate as a I2 divided by the I1. See here the representation, here the 1 2, okay, 1 and the 2, here the 2 and the 1, so 1 and 2. So here is nothing but if you're talking about the 1 and 2 means you are observing from input side, and the ratio will be the output to the input. Similarly, here we are observing from the input side and the ratio will be the output to the input. And if you are observing from the output side, that is the second phase. So here will be the you are looking from the you are taking the ratio of the input to the output. Likewise, in the current transformation denoted by the alpha. So in this way, in the frequency domain, you can get it. Again, the transformation in terms of the impedance is also possible, that we have studied in many of the cases. We have learned, we have taken the things, that is z is nothing but the representation of the impedance, and 1 and 2 apostrophe s is nothing but the what we can say the voltage as well as the current. Z is nothing but the ratio of v and I. Z is nothing but the ratio of voltage as well as the current. If you're talking about the 1 and 2, definitely the that ratio is nothing but you are looking, you are observing from the input side. So the v by I, that v by I is nothing but the ratio of voltage and the current, which is the definition, basic definition, or the what we can say the formula of your the impedance. So 2 and the 1, okay, that is output divided by the input current, okay, that is in the frequency domain. Similarly, if you are at the output side, you are observing from the output side the impedance. If you are observing from the input side, definitely the potential which we are going to consider, that should be the input, and the current which is flowing from the output side, so that is in the form of your the frequency domain. Similarly, if you're talking about the transformation or the transfer function of your the admittance, that is nothing but the y. So again you need to take care about the terminals, that is the 1 and 2 and the 2 and the 1. Okay, so here again the vice versa case with your the impedances. What is that impedance is vice versa, whatever you are taking here is a 1 2, the v2 divided by the i1 here will be the opposite. Okay, here will be the opposite, that the instead of voltage here will be the current, and instead of current here is the voltage. Okay, uh, okay, only the notation will be the same, that is a 2 and the 1 will be the same, but the instead of the voltage current will be there, and the instead of current voltage will be there. In this way you can find in the frequency domain. Similarly, that is a 1 2 and the 2 1, same I divided by v. In this way you can get I divided by v, and the notation will be again the 1 and 2 with the, if you compare with this z of 2 1, that is 1 and 2 will be as it is, but instead of voltage here is the current, and instead of a current here is the voltage. Similarly, if you are going to simplify how we can solve the transformation or the network function or the transfer functions, while if you are having the network or the circuitry of your the RLC, at that time how we can simplify for, in the frequency domain. So that is nothing but here how, what will be the numerical, how that will be representation of that numerical, how we can simplify that numerical if you are having the RLC circuit and you want to simplify in the frequency domain. So that is nothing but determine the driving points of the impedance function of your the one port network shown in figure. So here RLC is mentioned. Okay, if you are looking from here this side, definitely my voltage source will be here, and you are observing from this point, and the current will be start to flow from this point, and at this node, at this particular node there will be the division of the current. Few amount of current will go ahead, few amount of a current will go ahead, likewise coming from this resistor to the inductor, that is in the series form, whereas other current is flowing in the capacitor. So in short you can say the R as well as L are in series, whereas RL is in parallel with your the C. RL is in parallel with your the C. So see here how we can convert, how we can transform the network. So we are, if we are looking from the here, definitely we are talking about the voltage and the current, and the ratio is nothing but your the impedance. So that's why I have written here Z of S, that is in the frequency domain, and the capacitor will become as a 1 by CS. Already we have seen in the transient response and all. So R will be as it is, but L will be L of S. L will be L of S, C will be 1 by CS, R will be as it is. If you recall your own memory, and if you are trying to remember the transient response, steady state condition and all, you will be able to find how we can convert your RLC in the form of your the frequency domain through the time domain, how you can convert from the time domain to the frequency domain in short. So here the C will be your the 1 by C of S, whereas the L will be nothing but the L of S, R will be as it is. So how we can write the expression in terms of the impedance, Z is nothing but V by I. So voltage drop across. So in short you can say these two are in series and they are in parallel with this one. So in short, this is addition, um, these two are addition, multiplying with your the capacitor divided by addition of all. That is nothing but simple example I will give. If you want to do the parallel circuitry, reduce the parallel circuitry, R equivalent can be find R1 into R2 divided by R1 plus R2. So in the first case multiplication, and in the denominator there will be the addition. So similarly same thing is here going on. R plus Ls are in series, that is they are in series, that's why they are combined, and they are multiplying with the capacitor, that is nothing but 1 by CS. Again in the next denominator they all are adding, that's why I have written here. So in the next line, that is nothing but after writing that thing, so how we can write, how we can segregate. So R plus in the standard form, so 1 by CS will come down, so here will be R plus L of S, R plus L of S divided by LC square plus RCS plus, this is in the standard form. By cancelling the few things, by adding, likewise you can finalize. So in the second case, finally here at this moment, finally here at this moment, what you will do, you will take out the 1 by C at one side, and you are trying to do in a standard form, in the standard what we can say formula. So how it is possible? So 1 by C, that is S plus R by L. Why I am taking the adjustment R by L? Because all these things are in the Laplace transformation. The formulas are in the Laplace transformation. Whatever you will consider the input, just like with the sinusoidal, the unit step, the ramp, whatever that the formula should be in the standard, then only it is possible to transform from the time domain to the frequency domain, or the steady state to the transient response. So each and everything we are trying to take in the what we can standard. So that's why we are trying, the meaning should not change even though you are doing the adjustment, but meaning should not change. So same thing here. So 1 by c we have taken, and in our numerator the s plus r by l divided by standard form, that is a first order, then the s square, and then the s form, then the constant value. Okay, s square, then the s, and the constant, that is nothing but s square plus r by l of s plus 1 by lc likewise. So we are trying to do, we are trying to simplify, we are trying to do the transformation or the Laplace transformation from the time domain to the frequency domain if you are having the RL system. Similarly, if you go for the next numerical, that is nothing but find the voltage transfer function of the two ports in network shown below. So see here, there are two sections. Here the input port and the output port, that is in the form of your the voltage 1 and the voltage 2, V1, V2, in the form of your the S, that is in the frequency domain, how we can convert it. And the current which is flowing here is the I1, and the current which is flowing from here is nothing but the I2. So I1 of S and the I2 of S. So R and the C are there. Okay, the C is in the middle and the R is here. So directly they mention here in the S form, that is nothing but the frequency domain, I1, I2, V1, V2, and in the form of here the frequency domain. So how we can find? By the voltage division formula. By the voltage division formula, what they are asking, find the voltage transfer function. For finding the voltage transfer, we should know what is the value of your the V1, we should know what is the value of your V2. Then only it is possible to make it in the formula, that is the output voltage divided by the input voltage, that is V2 divided by V1 is possible. Okay, so how it is possible to get that value V1 and the V2? That is possible with the help of the division rule. If you are interested to find out the voltage, definitely go for the voltage division rule. If you are interested to find out the amount of a current which is flowing in the I1 and I2, so go for the current division rule. Okay, so here we are trying that only. So see here, the V2, that is nothing but the particular voltage. I'm repeating that the voltage division rule. The particular voltage, that is nothing but the V2. Particular voltage is equals to, okay, particular voltage is equals to the source voltage or the total voltage. Which is my total voltage? That is nothing but my V1. So particular voltage is equals to total voltage into opposite component divided by summation of all. So what is my total voltage? That is nothing but V1 of S. What is my opposite to V1? That is nothing but the C, that is 1 by C of S divided by the summation of all means R plus 1 by CS, R plus 1 by CS. Similarly for the V2, you can go for the V2 if you're looking from here. So you will be able to find, if you're looking from here, you will be able to find what is my V2. That is nothing but only across the V2 there is a 1 by CS. Across the V2 there is only 1 by CS. So similarly, now write down in terms of the formula, that is voltage transfer function is equals to V of S is equals to V2 divided V2 of S divided by V1 of S, that is nothing but 1 by CS divided by R plus 1 by CS. Now get it in the proper way, that is nothing but 1 by RC divided by S plus 1 by RC. 1 by RC divided by S plus 1 by RC. So this one is sufficient. No need to solve further. Okay, go for the next. Determine the driving point impedance of the network shown below. Here the inductance and the capacitors are mentioned instead of the resistor and all. So inductor is here, the capacitor is here. So here the connected in series. Then the here this inductor is in series with your the capacitor, and these two are in parallel with your the capacitor, and all these things are in series with your the 2s. So same thing is going on. How we can find that impedance? Impedance is equals to, if I am looking observing from this side, what will be the my case? This is in series, that's why 2s plus 2s plus CL. Add this moment, there will be division of current. Add this moment, there will be the division of a current. What will be the case? 2s plus 1 by 2s. See here, 2s plus 1 by 2s. These are in series, that's why they are in plus 2s plus 1 by, and this term is in parallel with your the 1 by 2s. That's why this into this divided by summation of all. This into this divided by summation of all. That's why 2 plus 1 by 2s plus 1 by 2s. 2 plus 1 by 2s plus 1 by 2s. See. So in this way we can simplify this numerical by multiplying. Okay, you can get in the standard formula. That standard formula is nothing but 4s plus 8s cube plus 2s plus 1 by 2s divided by 2 plus 4s square. Still you just do in the proper way. Again, it's not a proper way. That is nothing but 16s raised to 4 plus 12s square plus 1 divided by 8s cube plus 4s. At the end, till the end, later on there is no provision to simplify that thing. So that is nothing but the end of your the transfer function. So simply what we are doing, we are converting in the time domain to the frequency domain. We are converting the voltage and the currents and the impedances. Okay, we are looking for the series and the parallel circuitry. We are trying to simplify with the help of either the Ohm's law, with the help of the what we can say the current and the voltage division rule. Similarly, next numerical, determine the driving point impedance. Determine the driving point impedance of the network shown below. So see here in the at the beginning we have studied about the RL C, then the later on the RL, then the later on RC. Likewise, the numericals are coming here. You may take in the RLC anything, the combination of all R, L and C. You may take R and L combination. You can take the R and C combination, and you have the option of your the L and C. So these are the possibilities by which you can simplify, you can solve the numericals of your the network function. So in this case, if you observe, previous was the L and C and the series and the parallel combination was changed. See here in this case, the capacitor is in series and the inductors are in parallel. Vice versa case of your the previous slide. Okay, if you want to observe, just get it. See here. So inductor are in series here in this case at the beginning, and the capacitors are in parallel. But vice versa case here, the capacitor is in the parallel here. Inductor are in parallel and the capacitor are in series. So how we can simplify that this capacitor and this one is nothing but the S and the S. Nothing means 1. So that's why 1 by S, 1 by S, S, S. Okay, nothing means again the here is the 1 value. The inductor value is 1 here, inductor value is 1 here. The capacitor values again C is equals to 1 is here. That's why 1 by, instead of taking the C, C is 1. The value of capacitor is a 1 farad, a microfarad. So that's why they have not taken directly the C here. Here also they are not taken the LS. Why? The value of L is nothing but they are treating, that is assuming the 1 Henry likewise. So you can assume yourself C is equals to 1 microfarad and the L is equals to 1 Henry. So no need to take here the 1 by CS and LS. Okay, directly you can take here the 1 by S, 1 by S, SS. And you are observing from this side, that is nothing but the impedance. We are interested in the voltage and the current. So see here how the current will start to flow. If I am observing from here, my current will be start to flow from here, going towards the capacitor at this node. At this node, the capacitor and the inductor are in series. The capacitor and inductor are in series, whereas this inductor is in parallel, because there will be the division of a current at this moment. Few amount will go ahead, few amount will go at the bottom, and these two are in series, and the entire term will be in parallel with your the S, and the complete section will be in series with your the 1 by S. That's why we are trying at the beginning 1 by S plus 1 by S plus S, 1 by S plus S, and this term is in parallel. That's why multiplying with S divided by summation of all S plus 1 by S, S plus S plus 1 by S entire term. So in this way you can simplify. Okay, so how we can reduce that circuitry? These are the possibilities to simplify the circuitry. That is 1 by S plus 1 plus so and so. Finally, then last but one is 1 by S plus S cube or 2 S square plus 1. And at the end, finally, you can go ahead. The order is increasing, S raised to 4, 3S square plus 1 and 2S cube plus S. This is the final term. Okay, so in this way you can simplify the things. Next is a find the driving point of your the admittance function of your the network shown below. Here the inductor, here the capacitor, and both are in series as well as the parallel combination in the one figure only, in the one network only. One is in the series and one is in the parallel circuitry. So L and the capacitor are in series, whereas L and the capacitor are in the parallel, and we are observing from this side in terms of the potential. In terms of the potential. So see here how we can observe the impedance, how I can write my expression in the form of here the impedance. So here this will add, that is a 3s plus 1 by 5 of s. This is the in series plus these two are in parallel. So s into 1 by 2s divided by s plus 1 by 2s. S into 1 by 2s divided by s plus 1 by 2s. So this term is in parallel combination. This term is in series combination. Add all these, so you will get slowly if you are going to simplify the numerical, you will get finally that is nothing but your the 30s raised to 4, 22s square plus 1 divided by 5s plus 2 into s square plus 1. Later on, if you want to find out the admittance, because the question is here, find the driving point of admittance. We know very well y is equals to 1 by z or z is equals to 1 by y, the vice versa case. Y is equals to 1 by z and z is equals to 1 by y. So in this way, y of s is equals to 1 by z of s. So what is my z of s? You can revert it. That is, the numerator will become as a denominator and denominator will become as a numerator, and you can shuffle and you can get the final. That is nothing but the 5s in bracket 2s square plus 1 divided by 30s raised to 4 plus 22s square plus 1. So in this way you can simplify the numerical. Now come towards the poles and the zero. Few properties and the conditions are there if you want to simplify the numerical on the basis of your the poles and the zeros. So here the coefficients in the polynomial will be there. So n as well as the d, that is a notation of numerator and the denominators, things will be there. Here the combination of the real as well as the imaginary part along with your the poles and zeros. So you should identify which things are real, which things are the imaginary, how we can represent in the polynomial, and how we can write in terms of the ns and the ds. N and the d is nothing but numerator and the denominator. S is in the form of your the frequency domain. That's it. So here will be the, we need to simplify the order. We need to observe the degrees of your the ns as well as the ds. We need to observe the what is the voltage and the current transfer functions. Okay, each things we should remember, we should understand, we should apply the condition, how to simplify the poles and zero, how we can identify. So how we can do it? So see here, obtain the poles and zero plot for the following function. So vice versa case, in the previous transfer function or the transfer function or the network function, what we have observed, there were a circuit and we have tried to simplify, reduce that circuitry in terms of the Laplace transformation or the, you can say, frequency domain. Here the vice versa case, here we are not having the circuitry, we are having direct equation. We are having direct equation and we are trying to solve that equation to get the, to find out the poles and the zeros with the help of the s plane, which we have studied in the previous lectures. Okay, so how we can do it? See here, f of s is a one of the function in the frequency domain. The equation is s in bracket s plus 2, then the denominator is s square plus 2s plus 2. So how we can reduce the circuit? F of s is equals to s plus 2. Here the order, change the order, s plus 1 plus j of 1 plus plus 1 minus of j of 1. So this s square plus 2s plus 2 is divided into these two bracket. Now the function f of s has the zeros at how many s is equals to directly 0, s is equals to minus 2 is here, and at the pole, because already we know these are nothing but the zero. F of s, that is a function in the frequency domain. Z divided by p, z is a zero function, p is a pole function. So z by p, z by p, okay, z by p. So z will be representation of your the ns, p will be representation of your the ds. So likewise, so see here in the first numerator, s is equals to 0, s is equals to minus 2, whereas here will be s is equals to minus 1 minus j1 minus 1 plus of j1, because s is equals to, we are interested, s is equals to, if I am doing this, s plus 1 plus j of 1 is equals to 0 for this bracket. So finally what will be my s? S is equals to minus 1 minus j1. For this bracket, s plus 1 minus of j1 is equals to 0. How we can find this? S is equals to minus 1 plus of j1. So here in this case, minus 1 minus j of 1 and minus 1 plus of j1. So these are nothing but the real and imaginary part. These are the real and these are imaginary. How we can plot same things by observing all these things in the S plane. See here the S plane, this is the conductivity that is in the real form, whereas the j omega angular frequency in the form of the imaginary. This is the real and this is the imaginary part. Conductivity is the real and the imaginary is nothing but the j omega. How we can plot that starting from the 0? See here, the circle representing the 0 form. So s is equals to 0 means here is the 0. S is equals to minus 2. With the help of graph, we remember, keep in your mind the graph. S is equals to minus 2. So starting from the 0 to going towards the tentatively at any place you can go ahead. 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, likewise at infinite. Okay, So see here how we can represent the imaginary, that is nothing but the j form. J is at one time minus j1 and at one time plus j1. So see here for the plus there is a upper portion and for minus there is a bottom portion. So plus j minus j, plus j minus j, and the pole representation in the cross and the zero representation in the circle. These are the two circles and these are the two cross. Likewise in the dotted you can represent the x as well as the zeros. Go for the next numeric. F of s is equals to s in bracket s plus 2, and here is s plus 1 and s plus 3. So the function f of s has the zeros at s is equals to 0, and this s plus 2 is equals to 0, so s is equals to minus 2. Denominator s plus 1 is equals to 0 means s is equals to minus 1, s plus 3 is equals to 0 means s is equals to minus 3. Getting? So see here s is equals to 0, minus 2 are nothing but in the numerator is nothing but the 0, denominator are nothing but the what you can say the poles. So the zeros are 0 as well as minus 2 0 and the minus 2, and the poles are denoted by the cross. So minus 1 here is the cross, minus 1, and minus 3 is here, that is a cross. So cross representing the poles which is in the denominator, 0 representing the 0 which is in the numerator. Okay, in this way we have on a s plane we have drawn the zeros as well as the poles by concentrating the real and the imaginary parts. So conductivity is the real and the j omega is nothing but the imaginary. Similarly go for the third numerical, s in bracket s plus 1 s plus 2 the bracket of square plus s plus 3. Now in the first case which is in the numerator, that is s is equals to directly 0, s is equals to minus 1, but denominator order is there, so that's why twice. So s is equals s plus 2 is equals to 0, so s is equals to minus 2. S plus 2 is equals to 0 means is equals to minus 2. So likewise minus 2 twice. Why? Just because of the bracket square. So s is equals to minus 2 comma minus 2, and this one is equals to s is equals to minus 3. S is equals to minus 3. In this way we can plot the draw on the s plane the zeros and the poles. Okay, the cross is nothing but the poles and the zeros are nothing but the 0, and the sigma is the conductivity and j omega is nothing but the imaginary. Similarly, s plus 1 order of square, s plus bracket of square, s plus 5, s plus 2, s plus 3 plus j2, and likewise. So the function of f of s has a zeros at s is equals to minus 1 and minus 1 by twice, just because of the s plus 1 is equals to 0, the bracket square is there, s is equals to minus 1 twice, s equals to minus 5 once, and the poles which are in denominator, s is equals to minus 2, s is equals to minus 3 minus j2, and here will be minus 3 plus of j2. So likewise you can plot the cross is the poles and the circle is the zeros, and the sigma is the conductivity which is nothing but the real part, and the j omega angular frequency which is the imaginary part. In this way we can simplify the numerical. See here the circuitry is there, we can simplify in terms of the z, we can multiply this, these two are in brackets, so 2 into 1 by 2, that this is ls. So ls is nothing but your the um, s term is there, so 1 by 2 of s, so that is nothing but s by 2, and this is in multiplying s by 2 into 2 divided by s by 2 plus 2. So in this with this one by s which is in the series with your the capacitor, so 1 by s. So in this way you can reduce the circuitry. So capacitor will become as 1 by s, the resistor will be as it is, the inductor will be s by 2. So likewise you can simplify, you will be able to find the values. S plus 0.25 plus j 1.4 is equals to 0. So what will be the case? This will be go there, that is a minus 0.25, and here also minus j of 1.4. So here will be the plus or minus. In this way you can plot on the s plane, that is the zeros as well as the poles. Cross is the poles, 0 is the zeros, and here the two values as you are getting plus or minus j 1.4. So one will be in the upper positive half and the second will be downward negative half. So in this way we have tried to explain about the transfer function, we have tried to explain about the poles and the zeros. So in this way we have studied the whole content related to the two-port network, that is nothing but the transfer function and network functions in terms of the Laplace, in terms of the poles, in terms of the zeros, with the help of the S-plane and all. Thank you so much.